Okay, so hello to everyone. I'm Vito Capucciolo, is Francesco Colucci. We are from the Soft and Biomimetic Robotics group of the Robotics Institute. We work with Cecilia Laschi, and we are in the Kōan group. That is the evolution of morphology and control for a Titan Manta ray.
Okay, so something more about Kōan. We had first to build a model of a manta with passively compliant wings and try to actuate it with a simple oscillator. Then we had to try to apply evolutionary techniques, in particular genetic algorithms, to optimize both the control and the morphology of the robot in order to evolve the optimal flapping. And then we had to try to set up a comparison between the evolution of the robot on the Earth and hypothetically on Titan. Sorry, so a comparison between the evolution of the same morphology and control on two different environments. So something more about the biological model. This is the manta ray. Manta rays are large eagle rays, so a group of cartilaginous species in the family of Mylobatoidae. And larger species live in the open oceans, while smaller species usually live on the sea bottom. And the larger species reach easily 7 meters in width. Particularity of this kind of animal is that they have triangular pectoral fins, two triangular pectoral fins. No, right? Still, two triangular pectoral fins that are used to actuate this cartilaginous morphology. So why the manta ray is a good case study for investigating the concepts related to this class? Because, for example, of the fact that the structure is underactuated, so the manta rays only actuates the pectoral fins with a quite simple control. And another interesting feature is that the structure is, for most part, passively compliant. So it strongly interacts with the environment. And with this interaction, complex emergent behavior are seen. So we said something about the biological model. This is our artificial model. So we discretized the fin of the manta with a modular structure. So this is a kind of modular robot. And we try to preserve the same geometrical proportion of the real manta ray. In order to implement the passive compliance, we modeled interaction between segments with spring-like forces. So we have torsion springs in the direction from the body to the tip of the wing, and linear springs that models interaction between adjacent chains, so in the dorsoventral direction. You can see, I hope that the system will allow you to see the video properly. This is a test, a threefold test of this passively compliant structure.
Okay. Swimming dynamics. The particular thing about our project, with respect to common project in Weavers, was that we had water. So our dynamics, our physics was in water. So we had to investigate ourselves on the dynamics of the swimming of these animals. The manta ray and the other kind of batoids seems to swim using a combination of two mechanisms. One is the flapping, like birds, that you can see in the bigger picture, in the bigger pictures in the center and the right top. That is a manta ray that is doing a sort of flapping, but in the right top you can also see that this flapping is not homogeneous along the fin, but it is also moving from the head to the back of the animal in a sort of wave. And in the right bottom of that there is another type of batoid that use prevalently a sort of ondulation mechanism, and so you can see that a wave that is traveling. The nice thing was that without discretization, we were able to preserve this mechanism, and it emerged from the interaction with the with the water, so was not set by us. We just moved the first chain of the discretization, the first chain that is the chain that is nearest to the head of the animal, and the interaction with the environment, prevalently the drag coefficient, drag force, was able to do this emergence of this behavior. You can see here a video that shows the movement of our wing, and that thanks to the interaction with the environment, you can see the wave traveling.
You can see both the flapping and both the waving, so yeah, the combination of the two.
As I said, this first chain is the only one actuated. All the other ones are just moved that way, just with thanks to the interaction with the springs and the reaction force of the drag with water. So how to model this fluid dynamics setup? This was really challenging. We read a lot of literature, and from some studies, in particular one from Clark and Smith, we saw that the mechanism underlying the manta swimming are vortices. These are practically impossible to model in a simulator like Weebles because they can't be modeled by local interactions. So we have to think about it and to say, okay, we have to do some synthesis. And so we moved from complexity to simplicity. How? Using some non-dimensionalization, using non-dimensional parameters. The most important two non-dimensional parameters were the Reynolds number, that is very common for all fluid dynamics problems, that is just the ratio between inertial and viscous forces, and the Strual number, that is instead a number that is characteristic of fish swimming. This Strual number depends on the frequency, as you can see on the screen, the amplitude of the flapping, of the moving of the fin, and the U, that is the speed at which the animal is moving, the fish is swimming. Okay, so what we did is, instead of having a moving robot that was too difficult, impossible to model, we just fixed the wing, as it is very common in the fluid dynamic experiments. We fixed one wing, and using the flapping and computing these parameters, we were able to reconduct to experiments that were done in a similar setup by Clark and Smith, and so to compute some quantities like the thrust. And we did this with on the two different planets. So on Earth and on Titan. What changed between these two? Fundamentally, just two parameters: the density, that is 1,000 kilograms over meter cubes on Earth, and 6.4 on Titan, and the viscosity. There is a difference 1.15 and 1.5 between the two planets. So we expected the Reynolds number to change, the drag force to change, and this to give an influence, to make an influence on the behavior and on the combination between flapping and waving. So how did we set up the optimization after this consideration? We know that the most important parameter was the Strual number, because we worked at fixed Reynolds number that is fixed for this kind of fishes in constant cruise speed. At constant cruise speed, there was the speed that we fixed was 0.11 meters to second. And so you can see these two graphs on the right. They are very important. The one on the bottom is the Strual number versus a thrust coefficient that is proportional to the thrust. So this allows at a fixed Reynolds number to have the thrust just knowing this Strual number that we can take from our model using the frequency of actuation that it is for us a parameter, and the amplitude of waving of the bottom boundary. And the top one instead is the efficiency of swimming. This is even more interesting. This is the efficiency of swimming compared to the Strual number, and it emerged that the peak of this curve is near Strual number between 0.25 and 0.35. And this is like all fish do. All fish do the same. After a lot of experiments, scientists, fluid dynamics scientists, observed that most of fishes tend to swim between in this interval, within this interval. So we said, okay, we can change some parameters like the amplitude of actuation, the morphology that for us is represented by the springs between the elements, and the frequency of actuation. And we use it as output parameters, thanks to the simulation in Weebots, the amplitude that I said before of the bottom boundary, and the digital number that is computed using these parameters. So our fitness was to swim at the highest efficiency, that is at Stuart number of 0.3. And so we tried to launch an optimization to fit this and see what changed between Earth and Titan.
Okay, some practical details about Weebot, the simulator that we had to use. We had to make an extensive use of this instrument. In particular, as I already mentioned, we had some challenges. We had to model a quite big modular structure. That is something that is not usually done in Weebot. We had to the necessity to model the fluid, some kind of fluid interaction. So we had to write a custom physics plugin, and we had to deal with the passive joints that were really important in our setup. We also found a bug in the simulator that we signaled, and it was fixed very quickly from the cyberrobotics guys that we want to thank. So the setup is depicted in the figure. We have the optimization algorithm, that is a genetic algorithm that runs in MATLAB and sends the genomes to a robot supervisor that runs in Weebot. The supervisor runs the behavior runs the robot with the specified parameters and computes the fitness as Vito was mentioning before, and returns the fitness to the genetic algorithm. Then there is also an interaction, quite particular, between the robot supervisor and the physics plugin. The robot supervisor sends some parameters to the physics plugin that is in charge of modeling interchain interactions and to implement the fluid dynamic model. So these results are really preliminary because unfortunately we ran out of time. So this is a single run that we launched last night, quite late in the night. But the results are encouraging because we can see some kind of convergence, and we can observe the best evolved organisms. This is with the Earth parameters. So you can see that the behavior of the robot is quite natural. You can see both flapping and waving. And you can see that the structure is quite similar to the one of a real manta ray, so it is quite soft. And you can observe the two undulation we mentioned before. On Titan, we had very some time to interpret the differences between Earth and Titan, but we can see microscopical the difference is that the frequency is different. So on Titan we have a lower frequency, and the wing seems a little bit softer. Yeah, a little bit softer. So we have to spend more time interpreting the differences, and we also have, of course, to evolve better organisms. But this was the first preliminary interesting result. So
for the future, we have a lot of nice ideas. We want to improve the fluid dynamics, getting the thrust from the simulations, and using it to optimize a certain thrust needed to move at a certain cruise speed. And then, why not? We want to build our Manta robot. You can see some examples of Manta robot built from Festo and a university. I think it's Virginia University. With that robot, we want to do some evolutionary robotic studies. So, because we saw with this study that a structure like this of a manta can change its behavior to can adapt to different fluids, we could do it on robots. And looking if they, at the same way they change their behavior to adapt to different viscosities or density of fluids, like, I don't know, swimming in some oils or some other kind of fluids. That could be very nice. So, thank you for your attention.
Thank you.
It was nice.
Okay, thank you. All right. I have to say it's quite an impressive piece of work you done. It's been fun following the project and very impressive. So I'll open the floor. Okay, we need to mute the mics, guys. Someone has a mic open. Okay, thanks. So if anyone has questions now, I'll open the floor for the teaching assistants. Let's see, anyone? Okay, doesn't look like there's anyone yet. So I'll start asking some questions. So one thing I wasn't quite clear on, maybe I didn't pay enough attention, but what modification did you have to do in the physics plugin because you based yourself on the Salamander physics, right? Can you describe a little bit about what you had to do to alter those physics?
So you're asking what we implemented in the physics plugin, what custom physics we had to implement?
Yeah, exactly.
Okay, so we had to implement basically two things: the interaction with the fluid that was modeled with the drug process computed by considering the velocity of the movement. And we also delegated to the physics plugin the modeling of the interchain in spring-like interaction. So the springs, the linear springs that model the interaction between adjacent chains, where for chains I mean the interconnections of segments in the direction from the body to the tip. So this was modeled in the physics.
I think that a nice thing was that we were able to export some of the knowledge of the physics of the swimming outside the program, outside Weebots. And in this way, we avoided a problem, a limit of Weebots in simulate some kind of physics.
Right. Excellent. So, would you? I mean, you've got quite a bit of code now. You got an environment. Would you be willing to make this open source? To make this project open, to put it online? Is that something we could talk about?
Why not? Open source is a good thing. So yeah, spreading ideas is nice. So maybe we'll do this.
Excellent. I think it's a very good project. I think that'd be fantastic. Any questions from the other TAs?
I have how did you cooperate in the group? Were just you or also the other member of the team cooperated?
This is a difficult question. We can say that we presented our own contribution.
Yeah, that was our work.
I don't know if someone else is going to present something.
Actually, you mean that the group, this work was from you, you two.
Yeah.
You. Okay. Nice to know. Anyway, great job.
Thank you very much.
By the way, how you would? I think you could generalize to fly in the air also, right? To a certain extent.
It's easy with the not very hard.
Okay. Any more questions?
Hello.
Yep. Go ahead.
First of all, I would like to say that it's really great work. I really enjoyed listening to your presentation. And I'm curious about, did you have any difficulty linking the MATLAB with the Weebots?
Well, yes, it was done really roughly, this night, really late, so it was not hard, but it is not the more elegant setup. So we are planning to modify this. So the interaction is mediated by files. So basically, MATLAB writes the genome in file, starts with it, with the parameters, and write the fitness in another file that MATLAB reads. This is not the most elegant solution, but it works quite well.
It was almost for yesterday, we had short of time.
Yeah. So anyway, there are several ways to interact between.
Yeah, sure.
So this is possible. Yeah.
Thanks. Great work. Thanks.
Thank you very much.
Any more questions? Okay. Well, thanks again, guys. It's been very nice watching your work. Finally moving and optimization as well. It's been really enjoy that. So with that, we'll move on to the next group.